Okay, the floor is yours.
Okay, let's continue. Okay, so like I said, I'll be presenting essentially the latter half of my thesis. So I came up with 3 different tools throughout my thesis, and this is the last 2. Yeah, so I'll start off. Well, so let's see. There we go. I'll start off by introducing guided waves in case nobody knows what they are and sort of how they're used in damage detection. Then I'll go on to some of the complexities and challenges that are faced because of fiber composites. Then I'll just talk a little bit about some brief physics on guided waves. I won't go too far into it because that's not really the point of this. And then the last 2 bits will be on the actual 2 tools that I was talking about. So one of which is a probabilistic decomposition of the wave modes, which is used to localize the damage. And the last one is a Bayesian approach to system identification using guided waves for an orthotropic model, which is a unidirectional fiber composite. So this slide is probably quite redundant in this group, but I might just go over it anyway, just in case. And because it helps to talk about where guided waves sort of come in, because guided waves have primarily been gaining traction in non-destructive evaluation rather than SHM, because some of the systems previously could take a while to operate, so they didn't really work very well in real time. But now with the advancement of certain products and different techniques, then they're started to be used in SHM systems as well. And guided waves offer a really good way of advancing up Rutter's hierarchy because of their low wavelength and high frequency. They quite readily apply themselves to classification or localization. So the actual use of waves themselves, here's a little image that might give you an idea of how they can be used to detect damage. So the PZTs are quite handy because they can both actuate and sense waves. So you can very easily switch between them. So you can build one matrix of sensors and that can be used for all of them. So as the wave propagates, it might hit the damage that you can see in brown here, and then the reflected waves in red then also get picked up by the sensors. So at the sensors themselves, you'll have what we call a wave packet. So that's both the nominal waves or the direct waves and the indirect waves or the reflected waves. So knowledge of how these are supposed to behave with and without damage is what's required essentially to be able to use these methods to detect and localize and even characterize the damage. It's quite an established field for orthotropic and homogeneous materials or isotropic materials. But when you get to different difficult geometries or difficult materials such as fiber composites, then there's a lot of additional complexities that really reduce the modeling capabilities that we currently have. Things like finite element models can work, but they're very, very intensive, and validation of those is quite difficult. Yeah. So guided waves in fiber composites, some of the additional complexities that happen is you get a steering of the group velocity. So dependent on the propagation direction, it will change the actual velocity of the wave itself, which, as you can probably intuitively imagine, that really affects our localization. You get additional damping from the epoxy matrix as well as the fibers. You get wave scattering from the fibers, continuous mode conversion. I won't go into details about these, but you can see that there's a number of complexities that appear from that. Some different approaches that people have taken to try and address these complexities is using high fidelity numerical or computational models, but you can imagine that that's a lot of computation power, takes a lot longer. Some machine learning approaches, there's been the classic, let's throw a CNN at this, or there's been a combination of both. And I think what I'm trying to do is I'd like to see it as a combination of both high fidelity modeling and machine learning approaches. So here's a little GIF, not a little GIF, here's a GIF of when it starts, there we go, of the wave scattering in a plate. So you can imagine for an aluminium plate, for example, it would be a nice circular wave, but this is a 90 carbon fiber weave. So if we go back, it's not going to restart. You can see all the complex sort of wave scattering that happens there. So a key thing about guided waves is their dispersion curves, and these are really useful in anything to do with guided waves because they essentially tell you the velocity of the wave and the group velocity of the wave based on the frequency of your wave packet that you're sending out. So in blue here, we've got what's called the anti-symmetric wave modes. And in red, you've got the symmetric wave modes. So in a plate, for example, you will get this separation between anti-symmetric and symmetric. If it's just a surface wave, you'll just have one wave mode. But these are really, really useful to have. And these are, as you can imagine, very handy for localization, because if you know the propagation velocity, i.e. the group velocity of the wave, then that's required for this. And one final thing on the actual physics of guided waves themselves. So we can generate arbitrary dispersion curves. So these are usually solved using numerical methods or matrix methods and things like that. But if you want to get dispersion curves for an arbitrary plate that you can't generate a model for, or you want to get the actual experimental data for that, so what you do is you record the wave, all the wave packets as they propagate in one direction. So here you can see that. So you've got the propagation distance on the x-axis and the time on the y, and then you do a very simple 2D Fourier transform, and then you get a really nice image-based dispersion curve here. So you can see this one. So this one, when you do this, you get it in the wave number, but the wave number is related to the phase velocity and the group velocity using these equations here. So if you can use these arbitrary dispersion curves to generate decent models of your dispersion curves, then that's going to be really helpful for a plate that might be otherwise difficult to model. Okay, so now I'll get on to actually the first tool that I'm going to be presenting today. So this one was a probabilistic decomposition. So as I said before, guided waves can be really useful for localization. So in this instance, on the left, we have a plate. This is simulated data. And on the left, we have a plate with no damage involved at all. So you can see it's a nice spherical wave. And on the right, we have a plate that has damage at y of 0 and x of -75. You can see the little cross there. So you can see the reflected wave. So if we can use knowledge of the nominal wave, i.e. the direct wave, and the reflected wave, then we can determine the location of this damage. Yeah, so the arrival time of the reflected wave can then allow us to determine the actual location of this reflection source. But to do this, we need the group velocity, and that leads on to the next tool that I'll be talking about. But for now, we are simulating an aluminium plate, and so we can get nice models of the dispersion curve, so we can estimate quite well the group velocity as well. And for 2D triangulation, you'll always need 3 sensors. This is a very simple way of how to localize when you don't know the start of the reflection time. So this is just taken from acoustic emission techniques, when you have 3 locations where you know when the wave hits those locations, but you don't know the time from when it emitted from the source. So it's just quite a simple objective function that you minimize, essentially. I won't go into too much detail about this. It's not hugely important. Okay, so the first thing we need to do is then try and decompose our wave packet, which contains all of the modes, into our different modes that we expect nominally, as well as our reflected waves. So to do this, add 2 stages of decomposition. So first, there's a full field decomposition, and this is going to use the dispersion curves, so the arbitrary dispersion curves like we went through in the first couple of slides, and then single source decomposition, which I'm using Bayesian linear regression for. And the reason for doing these steps is there's a number of advantages. So we can actually get a distribution of the predicted decomposed signals rather than just what we think the signal should be. So that gives us a measure of uncertainty that we can actually either propagate through the procedure, or we can use to, I don't want to say validate, because it might be the wrong term here, but we don't almost validate our decomposition. So if our uncertainty is large, then we can actually have an uncertainty in our time of arrival as well. I'll show in a couple of slides as well that it actually produces inherent parametric features of the wave, so energy-based features that we can then use for damage detection, or even potentially for classification and things like that. Yeah. So first thing is a full field multi-mode decomposition. So like I showed before, we do a simple 2D Fourier transform to create the image data. And then we use a simple ridge picking algorithm. And then that creates a Boolean mask over the image data, which you can then use. You essentially use this ridge picking algorithm to pick the modes that you want to reconstruct. So in this case, we'll reconstruct all of them, but individually. And then you just reconstruct those by using the inverse 2D Fourier transform. So here's a visual example of what all those equations in the previous slide just meant. So the red dots on the left image show the actual ridges that we've picked. And then the right image shows after we've applied the Boolean mask. So we're essentially getting rid of all the noise data. So what we would do to reconstruct an individual mode is just select just select a single mode, and then the rest would be masked out, if that makes sense. Missing a slide there, apologies. So then once we've got the reconstructed time signal data of the individual modes, this can then be used to create a dictionary of our individual modes for a propagation distance. So in this case, psi of x and t is essentially our signal amplitude at a propagation distance x and a time of t. And then, so we form a linear model here with just a Gaussian noise epsilon there. And then, yeah, so the basis is formed on the different modes that you want as well. So in this case, we're just looking at the A0 mode and the S0 mode. So once this model is formed, it's very simple Bayesian linear regression technique to get these weights. And then we'll see in a second that these weights that you get, it's going to be a 2-element vector that essentially gives us the relative amplitude of each mode for that signal compared to our observed signal. So here's an example of this. So we've got at minus 90 degrees. So this is at the propagation direction directly towards where the damage was. And then at minus 45 degrees, obviously 45 degrees away from the damage. And we have so here you can see one of the advantages of the methods, which is the predicted variance is quite different between these. And this is essentially due to a mismatch in the spatial locations because of 90 and 45 degrees, because it's a square cell array. And so on the above image, you can see the reflected signal is there at between 30 and 40 microseconds. And that's quite far out of the variance of our predicted variance. So that's good. So then we're quite confident that this is a reflection signal and not just normal variance within the signal itself. Whereas at 45 degrees, the reflected signal at around 40 microseconds is fairly within the predicted variance. So we might not be as confident that this is our reflection signal and not just standard variance within the signal. So that's quite nice, and it's nice to get that straight out of there. So this is now on the inherent parametric features that we get from the decomposition. So as I said before, the weight vector becomes a 2-element vector, one representing the A0 mode and one representing the S0 mode. So what we have here is on the left is essentially decomposed, did the Bayesian linear regression decomposition at each propagation distance. And then the left one is without damage rather, and the right one is with damage. This is all in the propagation direction towards the direction of damage. And the red line here shows the actual location of damage. So we can see we get the weights themselves become quite noisy when we get close to damage. So that shows us that when we are decomposing at a location that is close to the damage, we need to be careful. So we need to make sure that we're using signals that are relatively further away from the damage. But one of the nicest things from this is you can see the weight of the A0 mode drops significantly straight after damage. And without diving too much into the physics of it, damage causes a wave mode conversion from anti-symmetric to symmetric, or vice versa. So this one is very clearly showing quite a strong conversion of this A0 mode, so it drops straight after the damage. What this essentially shows is that the weights that we get out of this are inherent parametric features that indicate the energy, and it matches the physics that we know. So that's really nice. And then now onto the actual localization. So once it's decomposed and we can get the start time of the reflection signal, using a simple AIC method, and then using the triangulation method, the optimization that we could see earlier. These are some examples. So we had different sensor layouts on this simulated plate, and these were the locations of the sensors. So and then the predicted location of the damage, which matches up quite well. In fact, reasonably well. This is expected because it's a simulated aluminium plate, but it's being tested on a carbon fiber plate now. So we'll see how that goes in the next couple of weeks. But we can see that it works quite well so far. So that's really nice. All right, and the second tool is a Bayesian approach to system identification using guided waves. So, so the general idea of this is the motivation behind it was that in order to do the localization, we need knowledge of the group velocity. And especially in fiber composites, because you have different group velocities at different angles. So in cases where the material properties are unknown, for example, in this actual case that I had where I got a plate from our industry partner and they didn't know the material properties and I didn't know the material properties, so I couldn't really form a model. So that was essentially the motivation behind this. So the idea is that from the equations of motion, the dispersion curves for an orthotropic model are defined by the stiffness matrix C. So if that's the case, then surely information on the dispersion curves could provide us information on these parameters in the stiffness matrix. So the reason for a Bayesian approach is that more than just a value, we can actually find the information on the distribution of each parameter, which can be very useful. And again, for propagating uncertainty quantifications through, and to actually see that the parameter effect on the dispersion curves are quite different. Previously, a genetic algorithm was used, which worked really well, and they did it on a matrix method. But what this did was it includes the variance as a parameter for which to optimize over, and it assumed a Gaussian posterior. Whereas here, what I've done is use a Markov-Chain, actually a Hamiltonian Monte Carlo, to simulate over the posterior distributions, which allows us freedom of these distribution shapes, which we'll see is important later on. And as well as this, it simulates the cross correlation between the parameters themselves. Previously, this wasn't really feasible because of the matrix methods that we used. And so they were really computationally expensive, and it was just a nightmare to run with Markov-Chain Monte Carlo. But now I discovered a Legendre polynomial expansion approach, which I'll not going to touch on here because it's quite long, but essentially what that meant was that the equations form out into expanded polynomials, which means that we can go at the problem, we can form these polynomials in a programmatic way. Previously, they'd all been done in a symbolic programming method, but as we could go at it programmatically, we could speed up the actual process. And so it became feasible for a Monte Carlo simulation. So in case anybody doesn't know what MCMC is, the general idea is you have a set of parameters that you're wanting to optimize over, and at each step in the simulation, you walk randomly, in inverted commas, in a certain direction for each parameter. But the random walk is set by a prior that you set on each parameter. So in this case, we can use prior knowledge of what is a reasonable elastic constant. So we're not going to say it's between 0 and 1. We'd say it's between 0 and 200 gigapascals. And you could give it a actual distribution over these parameters as well. And it includes a little bit of additional randomness in it that allows it to move in less likely directions as well as more likely directions, so that we can actually simulate the full distribution. I implemented this using Stan. If anyone's not used Stan, I would really recommend it. It's fantastic for probabilistic programming. It is a little bit of a horrible Frankenstein's monster of C, Python, MATLAB, but once you get the hang of the actual syntax, it's so handy. So I would really recommend using Stan. Okay, so first, how did we measure the arbitrary dispersion curves? So using a 2D scanning laser vibrometer, and then a stack actuator on the glass fiber. So we have a glass fiber composite plate. Should have specified that earlier. We have a glass fiber unidirectional composite plate, and it's the setup is shown in the figure on the left, and then the fiber propagation direction This is looking top down onto the glass fiber plate, so it's all heading, and we've set 0 degrees as the fiber propagation direction. And on the right is our arbitrary dispersion curve image in the direction of the fiber propagation. So you can see quite clearly we've got the anti-symmetric mode, the symmetric mode, and a couple of additional ones as well. But for this one, we're just going to focus on those first 2 fundamental modes, so the first anti-symmetric and the first symmetric. Okay, and then once we've simulated over these posteriors, this is the results in the direction of the actual, in 0 degrees, so in the direction of the fibers. So you can see quite clearly there is a strong, you can see the cross correlation between some of them. There's quite a strong correlation between certain parameters, such as C11 and a lot of the others. The one that had no correlation between all of them is our noise in our model. So this is not the noise of the distributions, this is the noise of our actual model between our measured and our predicted. The one that came as a really strong correlation was between the density and C55. And without diving too much into the equations, this makes a lot of sense when we are looking at the actual physical equations of this, because when we, as C55 is to do with the actual propagation between the top, is to do with the stress between the top surface and the lower surface, no matter which way the wave is operating, then those two are going to be the most interactive. Oh, how does it stop working? Oh, there we go. And then at 90, we get very similar results, but slightly different as well at the same time. So you can still see the cross correlation. One of the key things to take away from these 2 figures, though, is the distributions themselves clearly don't fit to one type of distribution. They're not. They look to me like gamma distributions. In fact, when you fit a kernel density estimate on them, they always end up as a gamma, which shows that we need to allow freedom in simulating the actual posterior shape rather than assuming it to be a certain type. And then, so as the motivation for this was to determine the actual dispersion curves themselves, we can use the simulated posteriors to generate distributions of the simulated dispersion curves, essentially, and then match those to our data points that we fed into the algorithm. So you can see here at 0 degrees, it matches up really quite well, and it lines up with the darker areas in the image that we can see to be the curves. And this is good, this is nice as well, because this can provide us an immediate distribution of our estimated velocities, which we can then propagate through to the localization technique. Now, the interesting one is when we look at the 90 degrees one. So for the A0 mode, it fits really quite well, but for the S0 mode, the model clearly is having some difficulty fitting to the points that we've observed of this curve. Now, this makes sense because the model that we've applied is an orthotropic model, which should only be applied in the direction of the fibers, because as soon as we go away from the fibers, the orthotropic model will break down. So that leads on to the future work that I want to do on this. So first thing that I want to do is improve the information that is provided to the actual procedure. So improve the bandwidth of the dispersion curve information, especially if we want to include higher modes as well. I'd also quite like to adapt the likelihood to use full image data rather than individual points, which you can see on here. And then linking back to here, how the model doesn't fit well with the 90 degrees one, I'd like to test rotation of the stiffness matrix, because then that will also allow for full identification of the stiffness matrix itself, rather than just the parameters because once you boil it down to an orthotropic model, you get a reduction of the stiffness matrix to just the parameters that you saw in the results there. Whereas I'd quite like to include rotation of the stiffness matrix, and then that would be a full identification over all the parameters. But obviously this is going to take some tinkering to really optimize the code, because there'll be a lot more parameters as well as a lot more data points and things like that. And then one of the things I'm working on right now is actually to determine a model for the valid elastic constant space. That one might be quite difficult to explain without going really deep into the equations that we're looking at, but that would be really nice to provide a prior, instead of individually on the parameters, the prior would be set over all the parameters together. So I think that would really help to speed up the algorithm as well. All right, thank you for listening. I hope that wasn't too dense at once. Let me know if you've got any questions.